Hello, everyone. Warm welcome to VIVA Plus User Meeting 2025. It's great to have you participate in this year's user meeting. My name is Jobin, and I'm joining today from Sweden. I work as a researcher at Chalmers, and I'm one of the developers of VIVA Plus. Today, for the user meeting, we have a lineup of speakers, and we have for theme of this year's user meeting, pre-processing and post-processing for most part. So we have Manu from Arup, Maria from Cadence, and Shinya from Chalmers, who would later on in the second half of the user meeting talk about tools for pre-processing and post-processing VIVA Plus. And to start with, it'll be Johan from Chalmers and myself giving a brief overview of what VIVA Plus has been up to the past year. For your information, this meeting is being recorded and will be made available on YouTube afterwards. Each speaker today would have about 15 minutes, and we will take the questions afterwards. We'll have about 5 minutes for questions. So if you have questions for the speakers, please put them in the chat, and we will we'll take them after the talk. Yep, that's what I had for introduction. And let me, before I give over to Johan, I will give a brief overview of what VIVA Plus is. Maybe some of you are not familiar with VIVA Plus and haven't used VIVA Plus before. And we thought it would be nice to give you an overview of what VIVA Plus is. Well, VIVA Plus is a finite element human body model. And what makes it distinct is that it is open source human body models. And during the development, and now as we prepare the roadmap for VIVA Plus, these are a few things we keep in mind, that we focus on selected details as required for injury assessment in virtual testing. That means for the VIVA Plus, we have some parts or many parts that are detailed, like the skeletal structures, the lumbar spine, as you see, the cervical spine, and so on. So these are selected based on what we need to predict injury and virtual testing scenario. We have a high emphasis on robustness. Johan would talk about this a little bit more, but we achieve that by ensuring that the elements and the models of high quality. You can see here 90% of our elements have 66% of our elements have above 0.9 Jacobian, and above 90% have above 0.8 Jacobian, for example. And that gives us a really robust model here. For example, 90 kilometers an hour crash for a pedestrian, 70 kilometers an hour delta V for a rear speed occupant. And right from the beginning, we also had this emphasis on equity. And as part of a model lineup, we have average female and male, and not just vehicle occupants, but also models that can be used for vulnerable road users. And every release we make, we have these 4 models as part of the model lineup. And on top of that, what also makes VIVA Plus distinct is its open science philosophy. We make sure everything we do is in the open. Our validation and all workflows are published as reproducible workflows. And we have an emphasis on community engagement. And that's the reason why we do this user meeting now. And having said that, let me hand over to Johan.
Thank you, Jobin. Let me see here. I will start by sharing my screen. So, can I get the confirmation that you see the presentation screen and not the other?
can see this
Thank you.
percentage. Yeah.
Perfect. Okay, so the main focus of my talk today will be about the NCAP CP550 HBM qualification. But I will start with a few more slides to introduce the VIVA Plus if we have new users or people that are interested in the models. Similar to Jobin, I work as a researcher at Chalmers in Sweden. So that's where I am today. So let's see. So VIVA Plus is a model, and already from the beginning we made a statement here. So many of the human body models today have started off as average males. When we did this, we started off by creating a model of an average female. And the reason, or at least one reason, is that a lot of statistics, injury statistics, shows that female are at greater risks compared to males when it comes to traffic safety. Another reason is that it's usually when we scale or when we morph models, in many cases, it's easier to scale them up than scale them down. So starting with an average female that we later on can scale to other sizes, that might give us benefits. That is not anything we have investigated, but in theory it could. So yeah, the base model focused on a vulnerable female population. All the validation, the post-processing tools and the documentation is licensed as open source. So this makes the whole model process very transparent. We have detailed skeleton for tissue-based injury criteria and then simplified soft tissue modeling for speed. So you can see here in the section of the model cut section that, or it's hard to see, but we don't currently at least have a separate definition of muscles and fat in the soft tissue. Everything is in one PAD, and also we don't have detailed organs within the thorax and abdomen cavity. The models are already from the beginning developed to be morphable. In theory, all models are morphable, but here we have thought of this when we lay out the mesh pattern, that we later on will morph them and reposition them to other postures, and most important, a standing posture representing pedestrians. And as Jobin also mentioned, much effort has been put into making the models numerically robust. And in addition to the high quality mesh or nice mesh, that also is reflected in material models, where we have tested material models, we have pushed them further than you normally do if you evaluate the injury levels, but all in order to make the model numerically robust. This slide shows the workflow that we have been using. So from the beginning, we started with average data. So this is also a bit different to most of the other human body models. So most human body models are based on a scan from a single individual. That single individual is usually average in the sense that they have an average stature and average weight. But when you come down to other measurements like arm length, seated to height ratio, and so on, they might not be average anymore. So instead here we have taken the original geometry from Amtri's statistical shape model, and this would be the same as the Hermes model is based on. So these are average data in a more general sense. Based on that, we created the base model, and that is the seated female occupant model. Next, we create derivative models and using mesh morphing. So we morph it to the seated male, to the standing female, and to the standing male. We validate the models both on component level and on full body level. And here we then select a model that best represents the validation load case. So if it's a validation load case of small females or average females, then we use the female model, obviously, for that validation, and the same if it's male models. After that, we continuously get feedback from end users. Could be that the model is still not robust in some area, could be issues with the positioning and so on. If we then need to go back and update the model, we go back and update the baseline model. And then by, again, morphing that updated baseline models to the derivative models, we automatically get all the updates in all these 4 baseline models. If we look at the detailed part here, rib cage has been one of the main focus from the beginning. Here we see the mesh pattern where we have a quite fine mesh for the ribs, a bit coarser for the intercostal muscles. The mesh is created in a similar fashion as for the SAFER HBM, and this was part of my postdoc a long time ago. So we have averaged rib geometries, we have average cortical thickness of the bone, and because the cortical thickness is quite thin for ribs, here we need to model that with thin shells. If we look at the long bones, here we see one example of the lower extremity, but it would be similar in the upper extremity, the humerus, the radius, and ulna. Because these typically have much thicker cortical bone, to make that numerically accurate, it's usually we have some limitations with the thin shell, as you probably all know. So here instead we're going for solid elements to represent the stress and strain distribution through the cortical bone. And here you can see one example of the femur where we have 3 elements over the thickness in the shaft region, and then at the ends of the femur, posterior and the 2 ends, then we go down to 1 solid element of thickness because there the cortical bone is much thinner. Here I just repeat one of the slides that Jobin showed. So we have here you see 3 different criteria: Jacobians, aspect ratio, and warping. And something that we think is important here is that not only the base model but also the derivative models fulfill our element criteria. So in the baseline models, all elements, 100% of the elements fulfill the criteria. So aspect ratio below 12, Jacobian over 3, and warping below 30. So this means that after we have done this morphing, we need to do some element fixing. We have a number of robustness load cases. These are for in-vehicle occupants, and these should be quite severe compared to what you normally run when you use the model. So the delta V is 70 km per hour, which is, it's at the upper limit at least of what the model should be used to. And the side impact that you can see in the bottom right is also quite severe. Okay, so on to the main topic for today, the NCAP CP 550 HBM qualification load cases with the VIVA plus 50% male model. The first message here, and the most important message, is that the VIVA plus 50 percentile male is qualified for the CP 550. That's the most important thing. If we dig into the details a bit more, you can find the results. So it's now included in documentation, and the documentation you can find on VIVA Plus readthedocs.io. And here you can find the link. So you see in the middle of the page, there is a link to openvt.eu. If you follow that link, you will get here. And here you can find all the results openly available. So this is fully transparent. I should also say that when we have run this, we have not done any tuning to the model. So the model is based on the validation we did before this. You can download both the models if you like to rerun them, and the notebooks, and you can rerun that at the computer. And this also means that during the setup of these different load cases, you need to specify some parameters, and those are HBM specific. By downloading here, you can check how we specify these parameters, so that is fully transparent. And if you don't agree to any of the settings, please report this to us, and we will have a second look at if there are more appropriate values. If we look into one of these folders, so here I've taken the show 2009, you will see a number of files. The most important one here you have the main Dyna input files. So these are general, so they should fit all human body models that are certified according to CP 550. But you need to do some modification based on your HBM. So here you can see how we have set the values, and this is typically sternum angles, for example. It could be coordinates of bones, anatomical landmarks, and so on. So in some cases, there could be a bit subjective how you choose them, but here you have the possibility to see how they choose them. We have Jupyter Notebooks, and Jupyter Notebooks, that's where you see the results. If you open that one, you can do that on the homepage, or you can download it and see it on your own computer. Here you will see all the results for the model. If you would like to rerun, then you need to copy the HBM files to that folder. So you download all of this, you download the Viva Plus, you put that into the HBM folder, and then you should be able to rerun it on your own computer. If you look into the Viva Plus catalogs, you will see that we have one validation catalog, and that has been around for a long time, for many years. And then we now have this HBM for VT catalog. And if you compare the contents of those, you will see that there is some overlap. So some load cases. Here, for example, we have Compagnia 2004, that is a shoulder impact. We have the Foreman 2013, that is a far side impact. Some of these load cases are located both in the validation repository and in the HBM for VT repository. So what is the difference then? Well, in the validation catalog, the main focus has been to replicate the experimental setups as close as possible for the VO Plus models. And that, according to me at least, is the definition of validation. We try to replicate a real experiment, and we compare the model to that. The certification catalog has a similar idea, that we want to replicate the experimental setup as close as possible. But we also have a constraint here that the modeling of the boundary conditions should be general enough to fit all human body models. And that can lead to some compromises. So that also means that the results can differ for the same load case, and the setups have slightly different purposes. So don't be surprised if you check the same load case in the validation catalog and in the certification catalog, and you see different results. In the future, your NCAP plan to tighten the certification limits in CP 550. So what does that mean for the Viva Plus 50M model, and how does the Viva Plus model compare to other human body models? To get a feeling for that, we can go back to, and this is from the publication this year from Markobi that Felix did. Here we have results from a lot of different human body models, how they vary in scores. If we now overlay the latest results from the Viva Plus model, and this is just a selection of them, I couldn't fit all to the screen. So the green dots here are the Viva Plus results. And if I point, I hope you can see here. So in some cases, the Viva Plus model performs among the worst, has the lowest scores, whereas in other cases it has among the highest scores. I did this yesterday, so these exact position of these points is not accurate. I kind of eyeballed them in based on it. So don't take this as 100% correct. But what I want to show you is that, yeah, in some cases where the model is among the worst, and in some cases among the best, and in other cases kind of in the middle. So if we average this over all the load cases, all the sensors, we can see that the VIVA Plus model performs slightly below average, just below average for the LIP score, and slightly above the average for the other score. So yeah, we could say that the VIVA Plus model is kind of average when it comes to the human models, not so much better and not so much worse than the others. Load cases and signals where the current VIVA Plus model is close to the lower limit, and when we talk, so when your NCAP will tighten the limits later, that means that the lower limit will move upwards to kind of push the human models to improve. So where the VIVA Plus model is close to the lower limit is where we need to update the model first. And we can see that it's some load cases and at some speeds. We have Compinia, low severity at an angled impact, so that's a shoulder impact. We have RUP, medium severity knee impact. We have Iraeus, rear configuration, pelvis rotation, and then we have Viano, so that's pendulum impacts to various body parts. The first two, here we see an example of the Compinia where we can see that, see here, so the simulation response is here, it's moving very small deformation, whereas the average of the test curve is higher load and higher deflection. This we kind of expect because right now we have a robotic joint in the shoulder, and this makes the model way too stiff. So this is something that is expected. The RUP is a similar issue. So also for the knees, we have things that are too rigid at the moment that needs to be improved. If we look at the Viano, and this is one example where we had a hip impact at high severity. The reason we get very poor scores is that we have like an initial hump here. So even though the second part or the later part kind of match the average, you get penalized by the arc length method because we're out of phase. So these black lines are corresponding points. So this initial hump means that we get out of phase and we are out of phase the whole signal. So even though it looks pretty good at the later state here, the score is not excellent. So the updates that we see that we need to improve the lowest scores is create more bifidelic joints, shoulder and knee. Check this early inertia contribution, because I think that it's mainly inertia that gives us these initial humps to the torso and the hip. And here, if you look into the model, we can see that the soft tissue, that is a combination of muscle and fat, but especially for the hip, that would be mainly fat tissue, that has a density of close to 1.1 grams per cubic centimeter, compared to the true density that is closer to 0.9 for adipose tissue. So by just correcting that, the reason why is that high is that that was one of the parts that was used to get the overall weight and the weight distribution of the model to match the target. Then it's the Iraeus pelvis rotation, and here I think we need to go back and try to understand better what is happening, because we had a PhD student working for 4 years on submarining and submarining prediction. So I don't think it makes sense that we are among the worst to predict this, because we have invested a lot for this. So here I think we need to go back and see why we're not predicting this. And we do have our own validation test up here that we can compare to and see if we think that something is off in the certification load case. That was all for me. And if you have any questions, you can write it in the chat, and I can try to start answering them during the other presentation also. Thank you.
We have some questions. Do you want to take one or two now, Johan, from the chat?
I can do that if we have time.
Yeah, okay, maybe we can do one or two and then we can come back later on for the rest of the questions.
Yeah. So let's see if I go into the chat here. Yeah, where should we start?
We have a question about VPS.
There is a question about VPS.
From Nissan.
There is a VPS version available. However, that is for an earlier version, the version 1 of VIVA Plus. We don't have a full VPS version of the latest one. We still haven't performed the validation, all the validation on that model. So that also means that it's not certified according to CP 550. We can take that with us. Currently we don't have it in the plan to do that, but we can see if there is big interest for that, we can reconsider. Next question here from Daniel. As far as I understand, user will be asked to provide a certificate of qualification. Is that certificate already available? No, it's not. I have asked Felix who at Graz about that, and he expects that it will be completed in a few weeks from now. But that is the same for all human body models. Then we have a question from, sorry?
Maybe we can take this one more, and it's maybe a more general question from the beginning of your presentation. Do you want to go ahead about the cortical bone?
Yeah, okay. How does the model scaling take care of the material properties like cortical bone density between 50 female and male, or say properties on intervertebral disc for males and females? So at least what I have read in the literature, there is usually not any difference on material level between males and females. The difference is mainly on the structure level. And the structure level meaning that the female ribs are a bit smaller and more slender. That's why they produce less resistance compared to the males. So currently we don't have any difference on material level, but in the scaling we scale the cross section and the other dimensions so they fit the targets for a female population. The intervertebral disc, I would say that I haven't seen any study showing that there are difference on material level there either. Generally, the discs of a male is bigger than the discs of a female, and that's what makes them more rigid or more stiff. If you disagree, please tell me that, and if you can point at some reference stating the opposite to what I am saying.
Okay, thanks, Johan. We have some more questions, and some of us from the VIVA Plus team would try to answer them while the talks are going on. Otherwise, we will have these questions answered and posted on the VIVA Plus documentation. Okay, let's move to the next one, and I will share my screen here. And Johan, if you can help me now, if you see the right screen.
Yes, it's the right screen.
Okay, thank you. Oh, I would talk a little bit about the open science philosophy that VIVA Plus works with, and how in the last 5 years since we have had the models openly available, how we have been working and what happens between releases, and how we prepare the model for releases and so on. So you get a bit of behind the scenes on what happens before the model is released. And when I see VIVA Plus team, who are we? We are a group of 4 in the maintainer team, Johan, myself, and Corina, and Mate. In addition to that, we have 15 plus contributors contributing to the development or validation or documentation, mainly from Chalmers and TU Graz, from Austria and Sweden. When I'm at conferences, recently I heard someone say the best part of conferences is the coffee breaks, and I tend to agree. And I often get asked is whether it's even possible for the industry to use open source models. I understand why this comes up. The vehicle industry hasn't really embraced open source the way the other big tech companies like Google or Facebook or Tesla have recently, especially within mechanical engineering teams. So I thought I'll share the story from that I saw last week to kind of give a picture of what happens in the open source world. This is Daniel Stenberg. He is receiving the 2025 gold medal from the Swedish Royal Academy of Engineering Sciences for his open source project Curl. And Curl is basically a small library that helps with fetching files over internet. And it's installed in almost all devices that connect to internet, basically our phones, laptops, cars, yeah, and even space. It's on the helicopter that landed on Mars a few years ago. And he was awarded for his contribution to engineering with this open source library. And another one is from PyTorch. This is the neural net library that was built at Facebook, or Meta, as it's called now. It's Salman Chintala, who led the development of PyTorch right from the beginning. He's stepping down. He wrote this in his blog this week. PyTorch it's used almost everywhere. You use GPT, you use image segmentation or computer vision and robotics. And it's used in a lot of fields. And what is interesting between these two libraries is Curl is maintained mostly by Daniel, and he has contributors from all around the world, but it's a small team working along with them. But PyTorch is quite a big team. Right from the beginning, there were engineers and researchers from industry and universities contributing to this library. And it's kind of used everywhere in the industry these days. And it kind of shows the potential of how open source libraries can be. Basically being robust, reliable libraries that industry can use. And this was the vision with VIVA Plus, that it is an excellent platform for researchers and as well as to be a reliable tool for industry. And 5 years since we released, I think we've managed to achieve that goal. Whether it gets picked up or not, that's another story that we have to see from the future. Well, VIVA Plus, all the development, we host it on an open repository on OpenVT. If you would go digging into OpenVT repository, this is what you would see. You would see these updates, commits, and it happens in these trees. You see what is happening with on the development branch, on the main branch, and what's happening before releases, and so on. On an OpenVT platform, OpenVT stands for Open Virtual Testing. It's a collaborative Git platform, GitLab platform where we host all our content. Johan showed this workflow, and I'm going to share a bit of workflow of what happens with the updates and this is a story from last year. We had just finalized the version 2, and this was presented at the Human Modeling and Simulation conference in Germany in around this time last year. And this was the release candidate. We were running robustness and validation load cases and so on. But right after we presented this, we found that there were some issues that we needed to fix. For example, the head mass, we wanted it to match with the version 1 because we didn't want to change, have differences in the validation and so on. So we had to adjust the densities of the tissues in the head to match the head mass with the version 1. And so this is what you could see here on the GitLab repository. You could see that we had something for release candidate 3, and then we go on to fix it before it was released as version 2, the stable, before we made stable release. And all those graphs and trees, what do they mean? I'll give a quick picture of how Git works. Let's say we have the version 1 and we are now working towards developing new features in the model towards version 2. For example, we had the lumbar spine that was done. We developed that in a European project called SafeUp, and Johan was mainly working with it along with Johan Davidsson and Yash. And in parallel, I was working with developing the new head in a Swedish project funded by the Swedish innovation agency, Vinnova. And when we had the model ready, of the lumbar spine and the head ready, it was time for us to make a release. We would work independently on different branches, and when it was time to make the release, we would make a release candidate on a different branch, and we run all our validation and robustness evaluations on that release candidate. And when we are sure of what the model is doing, we make a stable release version 2, which is then available to you as the end user. And since we work in the open, since the repository is open, all of this is visible to you as we are working in real time. You see how we are adding features and so on. And when each of those dots or nodes that you saw on the graph, those are called commit in Git language, in a Git repository. And each commit has a hash, a commit ID that identifies that commit. And if you would go to OpenVT, this is what you would see. And you would see who committed it or who changed, who committed the change. There's a description on what is happening in that commit. And more often we record the reason for the change and so on. For example, here there was a material ID that was not used rightly. And then you come to the file that was changed. It shows what was changed in the file. And so on. And then as you go, the next commit would then point to the previous commit. So you always have a version history of what is happening with the model. And this makes it transparent and reliable, in the sense you know what is happening with the model, with each commit and with each release. And the way we use the Viva Plus repository on OpenVT is like this. We use the issues feature for users to interact with us, the developers in the community. You could report issues, or you could ask questions, or make feature requests, and so on. The developers, we use a lot of features like Kanban boards there to plan and work collaboratively. And maintenance, we do all our preparations for releases and so on there as well on the repository. So you could say the repository in OpenVT is where Viva Plus lives. And if you have not seen what these version numbers mean before, the first digit, it indicates a major release. The second digit, it stands for a minor release. If you have smaller updates and so on, like changes to material properties or something like that. And the last digit are bug fixes. For example, recently we had to change the element format to be compatible with the Piper input. And there, nothing else is changing the model. It doesn't change the validation or robustness. It's just the formatting of the element, and that is released as the bug fix. And the last is something you would see only on the Git history. You wouldn't see that on releases. This is more for developers and the maintainers. RC stands for release candidate, and these are the versions that we make for testing robustness and eventually the validation just before you release. Make the release. I thought I will show you around on the repository so you know where to find stuff. For example, here, just before we made the release, we said modify the changelog and add download links for version 2 and so on. What does it mean? Let's go to the Viva Plus homepage. This is the documentation where we host everything. So you can come here to find all the information about Viva Plus. We have the validation tab where you can go and find the validation reports, HBM 4VT tab, where we have documented all the notebooks for HBM 4VT. There's a model documentation page and so on. But let's go to the home page, and there you would find the link to the repository. I cannot find it here. Open source, the models are hosted and maintained in an open repository in OpenVT. And if I click that on the new tab, this is what you would see. I'm not logged in now. And for example, here you have the changelog that I just mentioned. This is where we record all the updates and changes that we make to the model. And here it is, what I just mentioned about making the element format change to be compatible with Piper, and we just changed the last digit here. And version 2, what was changed from version 1, and we say what was added, modified, removed, and so on. And if you want to see the Git graph that I just mentioned, you could go to code here and go to repository graph, and that gives you a history of what has been happening in the model since we released it from version 0.3, which was the first public or stable release. And if you want to create issues, you would have to log in then, of course. Then let me log in. Then you would see an issues tab here. This is where we keep all our to-do list. And if you have things to, bugs you find, things you would like to see added and so on, this is one place where you could you can create new item and write down what you would like to see. And let's go back up here. And if you would go to Viva, the main folder, this is where you would find, for example, the HBM 4VT. And I have a lot of files here because, here, HBM 4VT here at the top, and LS Dyna, this is what Johan mentioned. And the validation load cases, they are in a folder called Viva Plus Docs. We just migrated to this repository so that we can have everything, all the validation HBM 4VT on a single doc rather than two different ones like before. And if you go into docs, validation, this is where you find all the validation load cases. Okay, let's come back to the presentation perhaps. And maybe I should show you where you could find the robustness also. If you go back to the main folder, you could find robustness. I'm trying to find here. Here. And these are the load cases we run before every release. So even for a minor update, minor release, we run all of these load cases, and the validation load cases we run for the major releases. We run for minor releases also if there's change in material properties and so on. We run the validation load cases, but for bug fixes, these are always run before the release. Good, and this is the validation catalog I just mentioned. Earlier, this was on a different website, and this is now integrated into VIVA Plus. And what makes VIVA Plus open is not that it is freely available at no cost. What we mean by free and open source is that you are free to run as you wish. You're free to study and change the model. You're free to share it with others, and you're free to share a modified version if you make modifications. And VIVA Plus, we have released it on LGPL license, which means when you share it with others or you share a modified version, you have to share it on the same license. But if to run or look at the model, there's no encryption or anything. There is you're free to do it. That's what it means. And for the validation catalog, documentation, HBM4VT, and so on, they all published under CC BY or Apache. And that means when you share it with others or you modify it and use it for your own use cases, perhaps you could do it under any license, and you don't. And even if you share, you don't have to make it public. You don't even have to make it open. That's what it means. And this is, I should emphasize, only for the models. It doesn't, it doesn't apply for your simulation or your load cases or your boundary conditions. These licenses apply only to the models. Good. That was that is what VIVA Plus is in a brief. That is what we have been doing over the last 5 years, working in the open, and this is what we mean when we say we follow an open science philosophy for our workflows, and as a team, I think this is what makes VIVA Plus unique in the HBM world. Let me see if there are any questions, or maybe I should end with saying what is happening in 2026. This is what you could expect. We have a new head model in Skull with a new Skull model that is prepared for tissue-based injury prediction. We will have risk curves coming out for that. The upper extremity, we are working on that on validation and tissue-based injury prediction. Active neck muscles, there was a PhD student who wrapped up now a couple of years ago, but the active muscles, they will be published for the version 2 in 2026. And of those, planning commercial support for commercial users. If you are interested in that, you could get in touch using the user survey that I will share in the chat. Yep, thank you for listening. I can take questions in the chat. Let me stop sharing. Yeah, running a bit behind schedule, and I suggest that we could jump to the next one, and if there are questions, I can answer in the chat. The next one, we have Manu from Arup. He will be talking to us about Oasys tools for positioning and injury assessment of VIVA plus HBMs. Manu, welcome.
Hi, I'm just going to share my screen. And let me know if you can see this now.
Yes, I can see your screen now.
Thank you. And hi, everyone. So I'm going to talk about the recent advancements for support of VIVA plus HBMs in Oasys LS-DYNA environment suite of software products. So this is the agenda for the talk today. We are going to talk about the introduction to safety tools in Oasys LS-DYNA environment. We are going to look at the overview of primer support for human body models, including VIVA plus HBMs. We'll look into the latest advancements in the HBM positioning support in Oasys, and we'll look at the injury assessment for HBMs in Oasys post-processing tools. Before concluding the talk, just a brief background on who we are. We have been working with ANSYS Elastana for about 40 years now, and we provide pre and post tools for setting up and analysis of the ANSYS Elastana simulations. We also provide technical support for ANSYS Elastana. A quick recap on the available safety occupant safety tools in Oasys Primer. So our ANSYS Elastana preprocessor Oasys Primer, it provides a comprehensive solution for occupant safety applications using ANSYS Elastana. This would include setting up various seat positions, deformation of the seat foam, while removing the initial penetrations between the occupant and the seat. It also includes fitting of the seat belts, including fully fabric seat belts through explicitly meshed slip rings. I've already opened the airbag folding and simulations video here, which is done using a third-party plugin called JFold. We also support positioning of the ATDs, dummies, and of course the complex human body models onto the seat in various orientations. Just a quick background on how the positioning is done in Primer. So as you might know, Primer can be used to prepare the human body models for ANSYS Elastana positioning simulations. The positioning of these HBMs is achieved using Oasys Primer positioning tree data. In the positioning tree data, all the logically related parts of the HBM are grouped together in what we call as HBM assemblies. Then the rest of the assemblies are connected using strict hierarchical parent-child relationships. So like if there is a pelvis, which is a root assembly, and then the thorax and the leg assemblies are going to be the child of the pelvis, and the head and the arms are going to be the child of the thorax, and so on. And I think my system is hanged. Sorry, just hold on. Bad timing, I guess. Somehow. Are you able to hear me?
Yes, I can hear you
Yep.
and see you and also your screen, but
I think
it isn't.
the presentation has stuck for some reason. Let me try and I'll just try and reshare. Okay. So, okay, I'm just going to restart the presentation again. Sorry about that. It might just take a few seconds.
No worries, can wait.
Come on. Okay, so just starting again, sharing the screen. No. Okay, it has come up now. Let's see. Let us hope it works well. Okay, let me know if you can see this again.
Yes, it's working.
Okay, I'll just run forward again quickly. Okay, so I was just about to talk about how the HBM assemblies are connected within Oasys Primer. So sorry for the delay. So now what we see here is a tree-like structure where the child assembly can just be connected to a single parent assembly. The permissible relative motions are allowed between these assemblies, and these can be set up using the DOF codes along XYZ axis. So the positioning tree that we provide are provided in an encrypted format. So this means some of the functionality pertaining to the encrypted beams, joint stiffness cards, parts, and others items in our tree file are not available. This is done to prevent access to the modify the tree metadata, which can prevent it from working correctly. But even though the positioning tree files are encrypted, you can still add new entities like shoes, helmets, etc. to the HBM assemblies using the primer edit assembly dialog panel. And this can help you in positioning additional components that you might want to attach to HBM during the positioning analysis. The benefit of this process is that the positioning analysis in Elastana would position the HBM limbs to the most accurate way. And this is done using the discrete cables that run from the initial reference position to the desired end position. So the red springs that you see in the animation that's running are the discrete element cables and are created by Oasys Primer. These cables are of course attached to the rigid material properties or elements in the HBM model, and these are created with finite length, which are then brought down to the zero length during the simulation analysis. And then the HBM is supposed to be positioned at the desired end position. The benefit here is that the simulation-based positioning helps us avoid the initial penetrations that might occur during more traditional rigid body positioning, and that's traditionally used for ATDs. Also, the simulation process considers the internal material properties and contacts that are defined inside the HBM and the vehicle. So this makes the simulation-based processing much more realistic. A quick walk through the HBM positioning tree family in Primer. So we support all popular HBMs on the market, including the VIVA and VIVA Plus HBMs, and we provide a full set of positioning trees for all these HBMs. And at the same time, we also have a complete set of mature HBM positioning tree development setup and processes that can be used to quickly support any of the future updated HBM versions. Within Oasys Primer, we also have a tool that's called the Visualization Table tool. It's an integrated material visualization interface that can intuitively visualize the internal organs and soft tissues within the HBM. This feature is available inside the software when the positioning tree file is loaded along with the original HBM files into the software. A quick walk through the positioning workflow in Oasys Primer. This simulation-based positioning analysis can be set up in Oasys Primer for a single stage, a two-stage, or multi-stage positioning analysis. First, you're required to determine the initial and the target positions for the positioning analysis. Then the Oasys Primer creates the discrete cable entities that are going to be used to pull the HBM limbs during the ANSYS LS-DYNA positioning analysis. And this helps in that the predetermined positions are achieved at the end of the positioning analysis. So with the help of the multi-stage positioning analysis using Oasys Primer, you can also achieve adjustment of some complex postures. Like we see here is a emergency knee hugging position in an aviation field. This is the process, the model was set up in Oasys Primer and run in ANSYS LS-DYNA. So now we are going to look into some latest advancements in the HBM positioning support in Oasys. So Oasys Primer now provides advanced tools to provide connectivity between the HBMs and the vehicular setups where these models are going to be positioned into. This could be the driver on a seat in various steering positions. It could be the reclined model in autonomous positions, or it could be a bike pedaling position as well. So Oasys Primer can be used to set up the various complex positions, and of course, these positioning analysis can also be set up using the automated script-based commands within the Oasys Primer. So this is one of the examples of the positioning analysis for VIVA plus HBM to achieve realistic bike positions in various orientations. Next is a quick walkthrough on circular assemblies. We introduced circular connections within the HBM and dummy assemblies for ATDs like Humanetics Thor, which was done to support the positioning of the clavicle. If I can get the pointer. So of the clavicle here is not connected if it is just a single one-way connection. So we provide a two-way connection, a multi-way connection where the clavicle and the arm assemblies are connected with the thorax assembly and they move in a more realistic way. So we have now introduced, just before that, this is done using the circular assemblies in the HBM positioning setup, where the child assemblies can now have multiple parents, where the extra connections between the assemblies is going to be achieved with a special type of connections that are termed as pin, line, or hinge. And this would create a circular construct amongst the assemblies. So this is now being introduced within the HBM positioning setups as well, where one of the examples could be to achieve biofidelic movements of the lower arm. To explain that, the upper arm is going to be the parent assembly. The radius and the ulna assemblies are going to be the child for the upper arm, and the hand is going to be the child for both the radius and the ulna, or it can be the grandchild for the upper arm assembly. And so it is so using these circular connections, the primer positioning trees, using the primer positioning trees, you can get the more biofidelic movement of the lower arm. It could be the rotation of the elbow, flapping of the hands, or if I can again get the point. So just to showcase how the wrist is moving without the circular connections when it is rotated laterally, and in here with the circular connections, the wrist moves along with the bone, arm bone. Another improvement or another addition here is to add extra cables for positioning. The positioning of the HBM assemblies happen by pulling these assemblies, and traditionally we allow up to 3 discrete elements to be connected to an HBM assembly. But it had been observed that some of the HBM entities sometimes get unnaturally deformed while pulling heavy assemblies like pelvis. It can also, in case of the hands and the feet, the finger and the toes would need more cables to be effectively positioned. So we have now given a way to be able to attach more then 3 nodes to attach positioning cables while performing the positioning setup. And these positioning trees can be customized for you if you need it for a specific purpose of positioning simulations. So we have been working on the injury assessment for the HBMs using the Oasys post-processing tools. We do integrate multiple modules around different regulations to directly generate the results and reports for regulatory conditions, including the model quality checks, correlation scores for simulation and testing, output damage curves in specified formats, and angle-specific video output. All of this is mentioned here. Of course, these templates can be used for different types of models. This is a project under development, that is being done using to prepare the HBM injury assessment templates, and we are developing the injury assessment templates for all the HBMs that are supported within Oasys Primer. These automated output templates are in line with the trend that may have HBM to be added to various procedures in the future. We have added HBM damage template on this basis, and we can output the various damage values that are required by the HBM and that might be required by the HBM protocols, such as the overall mechanical performance of the HBMs or the brain and rib cage damages. What you see here is a demo that we are still developing, and it outputs some of the damage values that are of mainstream concern at this point. And of course, if there is a definite regulation that is released in the future, we can also make corresponding modifications to adapt to those regulations. Another example of the head, brain, and soft tissues, and also the cross-section analysis. So this is for the brain and the cross-section analysis for the pelvis and the soft tissues. So watch out for this space in future. If you have any interested improvements that you want to have or you expect from our damage templates, please do reach out to us. So yeah, I guess we are towards the end of my talk today. In conclusion, we are making it quite fast improvements and advancements in the pre and post processing of human body models. We do support all versions of the popular HBMs. The Oasys Primer is used worldwide really by lots of clients. These positioning tree files that we had talked about are freely available to all our Oasys customers, and in future we'll continue to support more HBM versions for positioning in Oasys Primer. We are also looking to update the HBM positionings to be suitable for different scenarios. In addition, if the HBM is added to the protocol, we'll also support the HBM automated damage assessment templates that might be needed for those protocols. Yeah, so please feel free to reach out to us. You can write to us as well. Email ID is probably not flashing completely in here in the shared screen. Again, a problem with my system, I guess.
Thank you very much, Manu. If there are questions for Manu, please write them in the chat. We can take a few minutes to see if there are any questions towards Manu.
Okay.
Yeah, maybe people are still thinking.
Yep.
Yeah, please write them on the chat and Manu would be able to reply to you. Oh, there's already a question. Maybe you can take that before you switch off, Manu. There's a question from Tobias asking, for the post-processing, is there any general template available already?
So at this point, this is still under development, but yes, we can provide the beta versions if you want to reach out to us. Yeah, definitely.
Yep.
Hope that
Thank
helps.
you. Yeah. Thanks, Manu. Thanks very much. And let's move to our next speaker, Mori from Cadence. She's going to talk to us about ANSA and Meta. Welcome, Mori.
Hello, let me share my screen. I guess you can see my screen, right?
Yes, that works.
Perfect. So, hi everyone, thank you for the kind introduction. So today, on behalf of Beta CA Systems, I will present ANSA and Meta capabilities for HBM scaling, positioning, and injury prediction. So in ANSA, several tools were created specifically for HBM usage, the HBM scaling, articulation, and landmark positioning tool. And today we'll focus on this tool. However, I need to highlight that all crash and safety tools support the use of human body models. And then moving on to Meta, we'll see again a specifically designed tool for HBM post-processing. So I'm beginning with ANSA now. Three are the main tools for HBMs in ANSA: the HBM scaling tool that supports the morph of the HBMs to other anthropometries, the HBM articulation tool used to reposition the HBMs, at the HBM landmark positioning tool that's used to position automatically the HBM in a target posture. So let's begin with the scaling tool first. So the scaling tool can be used to generate an upscaled or downscaled variant model of the VIVA plus 50th percentile female or male. Here on the right, I have an example of the 50th percentile female HBM, where on the right, we can see an upscale version of the HBM to a height of 180 centimeters, and on the left, a downscale version of the HBM to a height of 150 centimeters. So in both cases, we can see that the mesh quality of the scaled models is still on the same level as the primary model. And the morphing in scaling occurs using a DFM morphing algorithm, which ensures coherent mesh and preserves model integrity. So in order to use the scaling tool, which are the steps? First, the HBM tool generates a target anthropometry. So the anthropometry is inserted by the user through a PTT format that can be outputted from Piper project. And this PTT format holds information of several anthropometric parameters of the human, like weight, BMI, length, or circumferences, which then are used on the scaling tool to morph the HBMs. So after generating the target anthropometry, a correlation between the anthropometry and the FE-HBM takes place, where we define some landmark points, some segments, and some sections on our HBM. And then we apply the morphing to our HBM. So the morphing currently is driven by the external skin surface of the HBM, and the rest of the body components are affected by the scaling. So muscles, bones, internal organs, and connective tissues are currently affected by the morphing of the skin surface. However, a new development that has been already fully developed and will be soon be available in a future ANSA version, has a new option, the controlled bone morphing option, which allows the morphing of the bone only along its longitudinal direction, and cross sections remain constant. So here I have an example, again with female VIVA Plus model, scaled, upscaled in both cases, on the left with the default scaling option, and on the right with controlled bone morphing option. So I think we can better observe the results through just observing the skeletons of the two HBMs. So on the left, the blue color depicts the default scaling, while the yellow color depicts the controlled bone morphing. And in areas where we have overlap between the primary model and the morphed models, we can see that the default scaling option in pelvis and femur, for example, has larger dimensions than the primary model, while the controlled bone morphing option has similar dimensions in pelvis and in cross-section on femur with the primary model. Again, seeing this from the backside, I think the results can be even observed, even better, where in controlled bones morphing option, we can see that pelvis has a similar size and shape with the primary model, and the rib cage holds its geometry, while the default scaling option widens the pelvis and the rib geometry, the rib cage. So a future development will be not only to have the bones fixed in one direction, but even to parameterize the morphing. So for example, for rib cage, and we're currently working on that actually, we're working on using some population data in order to morph the bones and morph the skeleton according to this data as well. And then if a user is interested on morphing specifically in more detail some areas of the HBM like head, pelvis, or rib cage, even more segments and sections can be defined in a PTT format and then used in the scaling tool. And now moving on to the HBM articulation tool. So the HBM articulation tool was the first tool supported for HBM usage in ANSA and offers a repositioning of the HBM in real time without the need of running a pre-simulation. So the articulation tool uses an advanced integrated multi-body dynamic solver in parallel with morphing algorithms. So we ensure the correct repositioning, the correct movement of the bones and soft tissues, and then the morphing of soft tissues in order to ensure the quality of the mesh. The HBM articulation tool offers a biofidelic articulation of the human body, and joints that articulate the HBM are used to articulate the HBMs are created in order to mimic the real human body motion. And the articulation tool works really easily just by adding an ANSA metadata file in the HBM. So here I have a few examples showing the capabilities of the articulation tool. We can see how the shoulder can be extended, how elbow can be extended or flexed again, the forearm pronation and supination, wrist movements, even finger movements are supported in the articulation tool. So finger movements can be kind of hold like a steering wheel in real time without the need of running a pre-simulation. And then hip motion is supported as well, knee and ankle joints, ankle joint motion. And here where we can see the skin surface, again, we can observe the really great quality even for large displacements of the body parts. And now just by seeing the skeleton of the HBMs, we can see that the bones of HBM are moving in a correct manner, in a realistic way, without adding more penetrations between them. And then, of course, the spine motions are supported in the articulation tool. Here we can see the spine lumbar extension and flexion, and in bones as well, where even the ratio between the pelvis and lumbar spine motion can be specified from the user, or like a max principal, max angle of pelvis can be again defined depending on the user's needs. And then for cervical spine as well, we support cervical extension and cervical flexion. And now moving on to the HBM landmark positioning tool. So this tool automatically articulates the HBM based on a given target posture. So usually this target posture comes from either volunteer measurements or crash tests, and the tool correlates the given posture points with the HBM skeleton points. Then, by utilizing the HBM articulation tool, the landmark positioning tool can articulate and position automatically the HBM in the target posture. So the way that the tool calculates the correct the correct posture is by computing the joints rotations that minimize the round mean square deviation between the HBM skeleton points and the target points as inserted by the user. So the articulation sequence of the tool is first to articulate the pelvis in order to ensure the correct orientation of the HBM, then to articulate the spine, then lower extremities, and finally the upper extremities. And here we can see an example of a bicyclist and how the HBM is articulated in real time in a bicyclist posture. And now moving on to meta. So as told before, in meta again, we have a specific HBM tool, the human body models post, where the user can select the HBM, like here, the VIVA plus HBM was selected, and have a list of the full injury criteria and the kinematics that can be outputted and calculated through the tool. So kinematic animations, injury calculation, strain plots, all of them can be extracted directly through the tool. And the best thing out of all is the automatic meta report, like a PPTX report, which made my work easier for today, as the rest of the slides are just slides of the report. So let's go through them. I'll showcase the meta capabilities with the bicyclist experiment as shown before. So we run the simulations and we'll go through the results to show how we can study injuries and extract injuries in meta. So by creating the PPT from the tool, from the HBM post tool, we have a full presentation with all injury criteria and everything. Here I've just selected a few slides of the presentation. And of course, we cannot go through all of them for today, but we thought that it would be better to showcase the injury criteria that are recommended by VIVA Plus developers. So for head injury, HIC criterion and damage criterion are the ones that are recommended, and of course both of them are supported through meta. And then for neck, the NIC criteria is supported as well. Here I need to highlight that this NIC criterion is not for this specific simulation of VIVA, but it's from another VIVA Plus simulations because it's mostly has to do with rare impact, so it didn't make sense to calculate that for bicyclists. And then for the thorax area, the fractured ribs probability is supported in meta as well, where on the right, on the table on the right, and on the plots on the left, we can see the max or the 99th percentile, depending on users' needs, strain that was calculated in each rib. And then this strain is translated to the probability of fracture of each rib, and again plotting on the left and with numbers on the table on the right. And then we can even calculate the probability of having N+ fractured ribs for our case. And these calculations of probability of fractured ribs can occur for different ages, for different age groups, by selecting the human age that we are interested in. Here we've run that for 25-year-old human, 50-year-old, and 75-year-old. And then, of course, animations for when and how much strains occur in each rib can be created and are created automatically from meta tool. And then for lower extremities, all injury criteria that are recommended by VIVA Plus are supported in meta. They were recently supported. So the femur shaft fracture risk was supported, and we can study the fracture of femur or the fracture of the femur shaft of the fracture of proximal femur as well. And then the tibia shaft injury criterion was recently added as well. So this criterion was not it was not published yet through a paper, but it's available in OpenVT platform. And for all injury criteria calculated in meta, the user can find the reference to the related papers on the lower right corner. So he has all information to go through the criteria and find out about everything he may need to. And then meta cannot won't offer only the injuries of the HBM, but will offer animations, kinematic animations of the HBM, either for the whole body of the HBM or for specific body parts. Animations, strain plots, and everything can be extracted through Meta. So that was all from my side. I'm open to any questions you may have.
Maria, if you check the chat, there are a couple of questions, I think.
Oh.
Or at least one.
Articulation tool. So for the articulation tool, because it's real-time articulation, the intersections are we handle intersections on the way we develop the metadata files. So we ensure that we do not have intersections of bones, and in most cases we do not even have intersections of other body parts, but these are not directly handled. So the intersections of bones are ensured not to occur through the way we develop the metadata files.
There's another question for you from Topias. Have you done any validation with the morphed models to confirm that this morphing is anatomically accurate?
So currently, no, the only validation was done. It's not actually referred to the VIVA Plus model, but was done with another model. And we've validated the model through morphing the male 50 model to the male 95 model, and then running some simulations, occupant simulations for that, and measuring some injury criteria. And we saw that we were in line with them, but of course more work is currently going on, and HBM scaling is like a newly developed tool with developing really quickly, and and a lot of work is currently going on with the validations, even on bones and everything, and there is currently working going on in this field.
There's one more question for you. Or maybe more. Have you made the comparison of prime and ANSA results to decide which one is more reliable? Oh, maybe that's a tricky one.
Okay, I'm not sure if if I can directly answer that. So yes, we have done some comparisons on that, and we would say that we have maybe in most of the cases better mass quality, but this depends, of course, of how many segments and sections are taken into account and all of these things, and yeah.
Maybe we can take one last question here from Tobias. It says preposition requires morphing of the soft tissue, so you prevent pre-simulation, where the occasions where pre-simulation was required instead of only morphing the flesh.
Yes, in some cases, of course, you cannot avoid like a marionette tool, which of course is offered through ANSA as well. But this depends on the areas you are more interested to study, and like maybe in some soft tissues and stuff like that, where you want to be really detailed on your outcomes. Then yes, in some of these cases, or when you need to ensure like the morphing of other parts, or like of vehicle parts, you may need to run a pre-simulation. But of course, there are multiple ways to avoid that as well, with the penetration tools and stuff like that. But yeah, always in some cases we'll need to run some pre-simulations.
Yep. Thank you, Maria. Thank you for the presentation and the discussion.
Thank you.
And we move on to Shinya, who's going to show us about Piper positioning.
Yes, thank you for kind introduction, Jobin. Let me share my screen first. Okay. Hello, everyone. My name is Shinya Abe. I'm a postdoc researcher from Chalmers University of Technology. I'm working on the injury prediction of vulnerable micromobility road users such as cyclists and e-scooter riders using the VIVA Plus model. And then here as my talk, I will introduce the positioning of the VIVA Plus HBM using the Piper, and I will share the practical information through this talk. And Piper metadata of the VIVA Plus now updated, and it can be used for positioning using the Piper. And then for the first time, Piper is not that straightforward to jump into. So considering that, we made a user guide and including the detailed step-by-step. So as long as if you follow those steps, you should be able to make the positioning model using the Piper. So if you go to the homepage of the VIVA Plus, you can find the user guide. Once you click here, you can find the positioning with Piper on the left column. If you click here, you can find the positioning with Piper for the user guide. And before we had only this overview, and then now we added the detailed instruction. You can find it here. And this detailed instruction was originally made by the people from our colleague from the Graz University of Technology, such as Dr. Christoph Leo, Professor Corina Plug. Thanks to them, and also thanks to Nico Erlinder, and as well as our colleague from Chalmers, such as Jobin John and Johan Iraeus, for their contributions. And then I will scroll quickly, so you will see this is quite lengthy step-by-step instruction here. So like I said, as long as you follow the step, you should be able to make the positioned VIVA Plus HBM using Piper. With given time, it's not possible to go through all of the steps, so I will go through some of the important aspects. First, Piper information can be found if you click these 3 links. And as the prerequisite before you start positioning VIVA Plus HBM with Piper, Piper is first can be found here if you click here, and you can download here. And sorry, I forgot to mention the Piper is the open source application. You can scale and also position the HBM, including VIVA Plus now. And the VIVA Plus can be downloaded here, but we would like to note that if you go here, you will go back to the home page of VIVA Plus, and you can download the VIVA Plus here. But however, I want you to be careful that if you click here, you would download the VIVA Plus version 2.0.1, which is the currently certified EuroCAP, as Johan explained in the beginning of today's webinar. However, the one compatible with Piper positioning is the version 2.0.2, which can be downloaded either in this repository on the OpenBT or by clicking here. So if you want to do positioning with VIVA Plus HBM, please click these places. And then Piper metadata can be available by clicking here. These and also necessary Jupyter notebook, which for transforming the positioning finite element simulation result back to the VIVA Plus model. These are available in the OpenBT repository again, but that's also available once you download the VIVA Plus model. And the next, once you start working on the VIVA Plus, positioning the VIVA Plus model with Piper, you need to set up the working directory. This is practical information. However, you need to set up your working directory where you need to put all the necessary files. It's because during positioning in Piper, you cannot change the directory. So you need to have one directory, and then you are not supposed to have any space. So for example, in this example, Piper and Triad are connected by underbar. So make sure that there is no space like given here. And then you can follow the how to set up the file setup and the folder. And once you open the Piper, you can load the VIVA Plus model and start positioning the HBM, VIVA Plus HBM. And positioning VIVA Plus using the Piper consists of actually two positioning process. And the first positioning process is this one. For this, I have semi-live demo, which I will play the video and explain over it. And from now on, I will talk fast, but all the information is available in the user guide. So if you cannot follow, you can still go back and check the user guide. So let's play this video. So first we open the Piper application and then import the VIVA Plus HBM through loading the metadata of the HBM. This may take some time, so I can forward. And once it's, sorry about that, once you've done that, you can also click the 3D view to check how it looks like in the Piper application. And then we will use this positioning module on the left-hand side and click the pre-positioning module. And loading this will take a few minutes. So again, I will forward a bit. And now it's pre-positioning module is loaded, and then we will activate the control panel, and we will disable the bone collision. Otherwise, you may run into the problem positioning. And we fixed all the bone which is not moved during the positioning. In this demo, I will only do the knee flexion of 30 degrees while the left femur is fixed. And then good method of positioning is that we found the joint controller works the best. So here in this demo, we will only move the left knee, and spring stiffness needs to be increased to maximum 1 in plus 10 to allow the large displacement. And if you click the flame, you can see the coordinate system at the joint so that you can decide which axis you want to rotate the specific joint. And now you can activate the positioning. Once you activate the positioning, you can increase the rotational degree manually, or you can insert number. Here you can see the leg is moving. And if you close, of course, you can see some skin distortion. However, you don't need to worry about it because Piper will only create the positioning finite element simulation input deck, which will be used as a boundary condition to simulate the positioning in, for example, in LS Dyna. So that should be taken care of. So that's the first positioning process. And then go back to the user guide. And what I have explained is explained here. And then in this user guide, a little bit more complicated positioning is involved. And the only goal of that first positioning is that it takes screenshot or record the final positioning, such as the degree of freedom of each joint. So here you can record just pen and paper or take a screenshot in the end of the screen. And you don't need to necessarily save the positioned model. And now we move on to the second positioning, which is called Python scripting in Piper. Basically, what this means is that the Python scripting will actually do the positioning for you, but you just need to specify the degree of freedom and also which joint you want to position. For this also, I have the demo, so let's get into that. Please let me know if you cannot see the video. And I will also increase the speed. And again, we do the same thing, import the VIVA Plus, and then this takes time to load and activate the pre-positioning module. And we repeat the same, fixing the bone, activate control panel, and then open the joint controller and add the left knee, change spring stiffness, add control. But this time we don't activate the positioning in control panel. This time we will use the Python scripting to position the VIVA Plus. So before that, we need to create a new folder. Let's name it export folder, where the piper will export the positioning finite element simulation input deck. And now we will do the activate all node and then turn on this toggle on and click the scripting. And you choose the first choice, which is positioning finite element odd.py. And the most difficult part maybe here is the specifying the argument. And the detail is given also in the user guide. And first argument is this directory including export. You just copy paste and add one backslash and one extra space. That one extra space is also important. I will get back to it later. And the second argument is import underbar model, and you specify next the joint you are going to rotate, and you put the degree of freedom there. And here you need the screenshot from the first positioning process. You have 30 degrees 0, 0, and 30 degrees just plugged there, and then you put two single quotation mark and put none for the degree of freedom, which was not moved. And lastly, you put the number of sub-steps you want piper to take in order to reach the final position. Here we put 3. And execute, you just open it. If there is no syntax error, there should not show any error. And here you can see successfully it executed the Python script. And then now we can finally activate position, and the first step is taken. And then now second step. And the third step to reach the final position. Now you can see the 30 degree is achieved. And now you can deactivate. And if you go back to the export folder, you should see the positioning finite element input deck is there, which is created by Piper. And that's about the second positioning process. So I will go back to the user guide now again, and that's all explained starting from here. And then tricky part, which is the how to write argument. If you expand this section, you can find all the necessary information. And using this, you can prepare the positioning finite element simulation, and all the necessary step is also explained here. And then ID numbers from the positioning finite element input deck, some of them collide with the original VIVA Plus model, which is at the default position. In this case example, I use the 50-year-old female standing position. And then I have also included how you can apply the ID offset. If you expand this one, you will see the explanation here. And also some troubleshooting before sending the job to the explicit finite element solver such as LS-DYNA. And then you can run the simulation. And once it's done, you need to transfer the nodal coordinate at the last state of the positioning, which we provide the Jupyter notebook. And this is originally developed by, again, our colleagues from TU Graz. Thanks for providing the Jupyter notebook. And you just need to follow the instruction given in the Jupyter Notebook. I will show how Jupyter Notebook looks like. This is a Jupyter Notebook, and you just need to follow these steps. However, one thing I would like to mention is when you run the Jupyter Notebook, make sure all Viva files, for example, in this case from 50F standing, and the Viva Plus from common folder, and a node you created by following this Jupyter Notebook, and this Jupyter Notebook itself, they need to be in the same folder. Otherwise, the functionality of this Jupyter Notebook, which is sort of the numerical issue, will not work properly. So make sure all the files in the same folder. And once you've done it, you get this position underbar nodes.k, and if you replace this one with the Viva Plus standing nodes, you should be able to reach this beautiful positioned Viva Plus, which is positioned so that it's about to kick the football. So this is how you can make the positioned model. And sometimes it might be difficult to reach the target position by just single run of the positioning with Piper. Then you need to run second and the third round of positioning. And there is something you need to do, and which I have also explained what you need to do. So just follow the instruction and you should be able to do that. And finally, I would like to announce that we are planning to make the tutorial video in upcoming months, which we will probably embed it in this user guide, or we will put it into the YouTube, for example. And then if you decide to do the positioning with positioning of Viva Plus using the Piper, and if you run into any problem and if you have any questions, we have the chat forum for that. At the homepage, if you scroll down, you can find questions. And if you click this drip, and on the left side, there's positioning. So you can ask the question here. And again, there's also Piper section here. So please ask questions. We try to answer as soon as possible. And thank you for listening. And this is all I have for today. Thank you.
Thanks, Shinya. There was a question about having Piper available on Linux, but Johan has answered it. We don't know Piper is available on Linux.
I'm not sure about the information might be available in the Piper's homepage.
Yeah, we're not sure of that. We shall wait for another minute if there's any other question to Shinya regarding Piper, positioning of Piper. And while we wait, I post a link to the Viva Plus user survey. So if you have the chance, we would appreciate that you communicate with us through this user survey about how you use Viva Plus, even if you're just exploring it. It'd be good to hear from you. It takes 2 minutes, and we'd appreciate your feedback. And as Shinya just mentioned, we use Zulip. Is one of the options you have to reach us other than email. We have channels here. For example, recently we started a new channel for the virtual testing updates, and any updates regarding CP 550, for example, would be posted here. And if you have questions, feel free to ask us here on Zulip or send us an email. Yeah, and we have different channels here, as Shinya mentioned, for the user meeting here today. If you've got more questions with the speakers, or for example, and so on. And this is what we as a maintainer team also use for development, doing development for communication, and so on. Are there any questions? Now the chat has disappeared for me. Doesn't look like, but you know where to reach us if you have more questions. thoughts for us. Before we end, it's my pleasure to thank again all the speakers, Manu and Maria and Shinya, and of course, Johan. Thanks for joining us today on this user meeting. And I look forward to seeing you either virtually or physically sometime around. Thanks, everyone.
Thank you.
Thank you.